Hello everyone, my name is Hooman Asadian, and in the following minutes I will talk to you about our work on applying symbolic execution to test the implementations of a network protocol against the protocol's specification. So we know that our world has become reliant on network protocols, and it means that the implementations of these network protocols should be thoroughly tested. One of these proven testing techniques is symbolic execution. What we know that it's less effective when it comes to protocol implementations due to the stateful nature of these protocols. So in this work, we want to present our methodology that makes symbolic execution more effective in testing network protocol implementations and exposing requirement violations using assumptions and assertions. We applied our methodology to test the implementations of the DTLS protocol, and our application revealed new security vulnerabilities and bugs in those implementations. So in this step, I'm going to give an overview of our methodology. Our methodology consists of 4 steps, of which these 2 steps are manual. In the beginning, we start by extracting these requirements from the protocol's RFC, and these requirements then are represented as logical formulas. After that, it's time to add assumptions and assertions to the SUT. We augment the SUT's code, software under test code, with these assumptions and assertions. More specifically, we assume that inputs under which a requirement can be violated, and we assert that no forbidden action is performed. So once we augmented the SUT, it's time for symbolic execution. So in this step, a symbolic execution tool explores the path in the SUT's code, actually augmented the SUT's code because we've already augmented it. And it looks for assertion violations, crashes, memory bugs, and so on. And for the test, for the passes, for the concrete test cases that expose an assertion violation or any other type of bug, we construct test cases, which we run against the unmodified SUT to validate that this bug really exists and it's not due to our modification to the SUT. So let me explain in more detail by giving some examples. So if we want to test the implementations of a network protocol, as I said, we start from the protocol's RFC. And we can identify the requirements with some particular keywords. These keywords can be must not, should not, and so on. We can identify 2 classes of requirements. The first class are input validity requirements that are concerned with the well-formedness of a sequence of inputs. We also have another class of requirements that are input-output requirements that are concerned with the outputs generated in response to a sequence of inputs. When we extracted these requirements, we just represent these as logical formulas. So let me give an example of an input validity requirement that we extracted, for example, from the DTLS RFC. DTLS 1.2 RFC states that for each received record, if they have a sequence number field, this sequence number field should be unique. So it's a uniqueness requirement for received records that have sequence numbers. We can, for a set of records that are received during a handshake, we can formulate this requirement as the following formula. That specifies that for each R and R prime that are not equal, the sequence numbers should be different. So now when we extracted this, it's time to augmenting the SUT with an assumption. So we have our formula, and suppose that in a handshake, we only have the following 3 records that contain the sequence number field. So we can specialize this formula for these 3 records, resulting in the following expression. So now that we have specialized it, it's time to assume the negation of this constraint. So when we assume the negation, this means that we are only considering a classes of input for which this requirement can be violated. So it is assuming that the sequence numbers are not unique when we are assuming the negation. So this is for the assumption part, and then it's time for augmenting the SUT with assertions. So in this step, we add an assert statement that checks that the implementation of the protocol does not process invalid input in some forbidden ways. For example, in the case of DTLS, we have that the invalid record should be silently discarded. And this silent discard means that we should not have protocol state progression in presence of invalid inputs. So how we can check that? It's a coarse-grained approach that we also employed, is that we can check this by seeing if we have invalid inputs. Can we complete the protocol interaction? In DTLS, you need all the packets to be valid to complete the protocol interaction, for example. So the way we can approximate it is by just saying, okay, in presence of invalid inputs, can we complete the protocol interaction? And we do that by adding a failing assertion to the part of the code that the handshake is about to be complete. Yeah. So now we augmented the SUT. Now we use a symbolic execution tool to explore the passes in the augmented SUT, and we look at, and symbolic execution looks for assertion violations, crashes, memory errors, etc. There are 2 challenges associated with our approach. So we know that symbolic execution suffers from pass explosion. So to alleviate that, we only make symbolic the relevant fields in a requirement. So in our uniqueness experiment, we only make the sequence number symbolic. And for the other fields, we use concrete values from a pre-captured session. Moreover, we only check one requirement at a time. So the fact that we use concrete values from a pre-captured session result in a new challenge, which is that we need to make sure that the SUT executes deterministically. To make that happen, we have to remove any randomization from the SUT's code to make sure that the symbolic execution is deterministic. So once the symbolic execution campaign is finished, for each pass, the symbolic execution tool returns a tuple of values for the symbolic fields based on the assumptions. For example, in our uniqueness experiment, we will have the concrete values for the sequence number in the participating records that contained the field sequence number. And for concrete values that cause bugs, as I said, we assign concrete values to the relevant fields. And why do we do that? Even we just want to validate that the bug, and we want to validate that the bug did not occur because of the modifications we did on the SUT. So we just run the test case, the resulted test case on an unmodified version of the SUT. Okay, we, of course, implemented our approach using KLEE. And applied it on the libraries of DTLS protocol. For each library, we built a test harness. This test harness is responsible for instantiating the client and server to capture the packets or records that are exchanged between the client and server. That's the one we use when we want to assign concrete values. It is then the test harness is used to symbolically execute the SUT in order to check for each requirement. Building test harnesses is a bit time consuming. So we developed some functionalities that can be shared between the different implementations that this shared library contains. Some helper functions for example, loading records from files, some functionality to parse DTLS records into predefined data structures, and also functions to make a specific fields in the record symbolic and forming Boolean expression in assumes and asserts. So now that I explained everything, we can put every piece together. If we want to, for example, test for this uniqueness requirement in a DTLS server, after building the test harness and formulating a requirement, and also adding the failing assertion to the server where the handshake is about to complete, we start the following. First, the symbolic execution starts with loading the records from files to the DTLS structured variable. Then we make the relevant field symbolic, and as you can see here, that only sequence numbers are made symbolic. Then we assume the negation of the requirement, so it means that the sequence number between these packets is not unique. Now it's time to feed the records to the server because we are testing the server in this scenario. And in bold, you can see the records for which the sequence number is made symbolic and assumed to be non-unique. And once the symbolic execution is done, we will have test cases. We see if we could, trigger the failing assertion, and also we check any other types of bug resulted from negating this constraint. So now let's go to the results. We have tested 4 DTLS libraries. We've tested two versions of OpenSSL, one from a stable branch and one from the develop branch. We also tested Embed TLS and 3 versions from 2 variants of TinyDTLS. In total, we could find 36 unique bugs, of which 6 are new security vulnerabilities. One of the security vulnerabilities is in the develop branch of OpenSSL at the time. The detailed explanation of the bugs we found can be found in our paper, but I'm going to explain a subtle one that we found in TinyDTLS now. So again, we started from the RFC. The RFC states that when a DTLS implementation receives the handshake message fragment, it must buffer it until it has the entire message. So I'm going to skip a lot of details here, but we formulated this requirement and did the symbolic execution. And we found the memory overread when the client or server, they are reassembling a fragmented message. This happens due to the fact that the fragment length field is greater than the actual size of the fragment. So it's interesting to mention that every time they submitted a pull request to fix the bug, we were able to trigger the bug in another way. And it took up to 3 pull requests until the root cause of the problem was identified and it was solved. I also have 2 experiences to report from using KLEE. So they are somehow related to protocol testing, but I guess they can be generalized to other applications. So we've noticed that generally in protocol implementation, they define the incoming and outgoing buffers with respect to the maximum transmission unit. So what does that mean? It means that when they have an implementation, the buffer they define is mostly the maximum size it can a message can be, but the message won't be that big for the most of the times. So if you receive, for example, if your buffer is 1,000 bytes and you receive a message which is 100 bytes, if you make some part of this message symbolic and you have out of bound of that 100 bytes for overread or write, KLEE cannot identify that for an obvious reason, because the boundary of the buffer is 1,000 bytes. But you have somehow an overread here, I would argue, because it's over the boundary of the message that is sent. So to solve this thing, we just allocate memory dynamically with respect to the size of the actual packet whenever we receive it. We've also noticed a significant interpretation, a slowdown, when functions in cryptographic functions are being executed. So this happens even in the absence of symbolic variables. We've actually provided a benchmark which has 700% slowdown. We have a partial solution that we are hopefully collaborating with KLEE developers to maybe make it better. Or partial solution for that is to execute the functions that impose a lot of interpretation, a slowdown as external code. It's still a crude idea, but hopefully it gets better. So in conclusion, we presented an approach to make symbolic execution effective for testing network protocols and exposing requirement violations by using assumes and asserts. The details of the bugs we found, the formulated requirements, and the comparison to other methods is available in our paper. Also, we have the replication materials available. And with that, I conclude my talk. Thank you.